Hello, we're just setting up here. We'll go start the office hour in about 5 minutes, but since it's our first one, we wanted to make sure that we set up. So I'm going to mute the microphone, and Aurora and I are going to finish starting up, and in about 5 minutes, we'll begin. All right, I think we're ready to go, and hopefully everything is working all right. And we are ready to start answering questions. A few of you have already typed in questions. So welcome to office hours number 1. Some of you are watching live. I can see you joining in right now. And some of you are going to be watching this at some point in the next couple days because it's going to be stored on YouTube. So I wanted to welcome you all to our first office hours. Aurora is here right with me, and she's going to be monitoring questions and kind of feeding them to me. She's, I would say, kind of like the producer, if you will, of this segment. So I guess let's get started. I'll tell you a little bit about what's happening here in Boston. about to send out the next video email telling you a little bit about some of the work that I've been doing this week. And we are really spending the summer where I don't have to teach as a professor, other than alien worlds, working with a bunch of different students and researchers on a variety of questions. And I think throughout the throughout the summer, we will be updating you about some of what we're learning, some of our adventures. When we go to travel to new places, we'll be letting you know a little bit of what we're doing and what we're learning. Okay, so let's begin with one of the first questions from the discussion thread. How about that?
Sure. Should I review the question?
Sure.
How about Fermi's paradox today? Does it mean we are alone?
So the question is asking about Fermi's paradox. And Fermi's paradox, if I can remember exactly, is one that says that basically, that aliens basically must not exist, because if there are so many stars in the galaxy and there's been so much time for civilizations to develop and for civilizations to contact us or even travel to come find us, we should have seen them by now, right? We got that pretty close. So why haven't we seen aliens? Well, I want you to remember, and most of you know this after just looking at the first module, that the distances that we deal with in astronomy are ginormous. So even if, let's say, you have life easily develop on lots of worlds throughout the galaxy, and maybe you get intelligent life developing, and maybe you get technological life developing. Remember, all those things have to happen. You have to have life, you have to have intelligent life, and you have to have that intelligent life develop technology to either communicate or travel through space. All of those things have to happen. And of course, that may have happened over the billions of years. We think our galaxy's probably been around for about 10 to 12 billion years. And so it's very possible that that's happened many times in our throughout the history. But you have to remember that it's very hard probably for it to not only develop, life may be easy, we don't know, and we'll talk more a little bit about that in module 9. But once you develop life, even if it's intelligent, which, I would say humans are intelligent. Some could argue that there are other species on our planet that are intelligent, things like dolphins, maybe some other of the primates, like maybe chimpanzees, some other creatures. People have made arguments that ravens are intelligent. That doesn't mean that they also have the ability to communicate through space. They have not developed the proper technology. And in fact, only humans who've been around for 100,000 years or so as Homo sapiens, we only have developed technology that allows us to both communicate through the vast regions of space and certainly travel a very short distance in space in the last, 60 years or so. So, maybe send radio signals a little longer, 80 years or so. And so, I think that I'm not sure I totally buy Fermi's paradox. I'm not sure it's that paradoxical that we haven't heard from an alien species, because the distances, the time it takes for not only a civilization to develop, but then to have the ability to send, understandable signals or travel to distant worlds may take a very long time. And to be honest, it's very possible that not all intelligent or technological civilizations may ever develop that. We have no idea. We have just the ability to communicate probably now with other civilizations just via radio signals. But those, to get to the other side of the galaxy take a huge amount of signal. And remember, there aren't going to be any aliens who speak English or any other language that's spoken here on Earth. And so we have to remember that there could be lots of alien civilizations who have tried to communicate with us, but that we didn't understand what they were saying. So that's very, very possible. And maybe someday we'll figure that out. we have no evidence that other civilizations have contacted us. There's some kind of fringe groups who maybe think that aliens have visited us and whatnot. I think that's probably not the case. There's no real strong evidence for that. But I probably believe that there's certainly life out there, and that probably there's intelligent life. Whether we would ever have the chance to communicate with it, again, given the vast distances and the time scale of kind of evolution, I'm not sure we would ever have the opportunity to do that. But boy, would that be pretty awesome. All right, next one.
So, if aliens are real and they visited us, like in the movies, it should be the end of human being. The aliens should advance than us in technology in huge distance so they can travel through the universe and easy to enslave us.
So the person asked, if aliens did visit us, maybe they would, they certainly probably at this point, if they did right now, would have much more advanced technology than we have. And so, some people worry that then they would not be benign, that they would come and they would enslave us or maybe wipe us out. There are actually people who are very concerned about this. They don't want us sending signals out to the universe, out to the galaxy to search or send signals out to potential life, because then that would tell these potential aliens where we are, and of course they'd come and get us. And I think that's certainly one possible view, but it's a little bit of a pessimistic view. Certainly, I think it's true that any civilization that could travel to us would be technologically more advanced than us. But you would hope that in that technological advancement, that they also might be socially more advanced, and they may have a much better outlook on the world, and in this case, the galaxy, and that they might be really benevolent, and they might actually want to help our species grow and evolve to a new level. So I think one possibility certainly is that they might be out to enslave or wipe us out or something like that. But I actually really think that a whole really very potential possibility is that, with the advancement of more technology comes a probably better self-awareness of one's place in the world, in the galaxy, and that you might actually have aliens who are want to help us as a species. So yeah, I think that's one way to look at it, but I think there's a more optimistic way to look at it too. Like I said with the Fermi paradox question, I actually don't think this is probably something we will have to deal with. Certainly in our lifetimes, and probably not as humans, but who knows, maybe. Yeah.
In the book, The Language of God, Collins tries to prove that a human like God exists. It is still a big debate today. As a researcher in astronomy, do you believe that God exists? If so, what does God look like?
Oh, wow. So this is a challenging question. It's a question about whether or not, I guess, and I'll answer it for my own self, whether or not I believe that God exists, and whether or not, if so, what does God look like? I certainly think that, there have been many times in the past where religion and science have kind of been at odds with each other, and I certainly do not find that they are mutually exclusive. I myself am not religious. I did grow up attending church and things like that, but I would say I'm not religious. I do find amazing awe in the way that the universe works, and the way that the galaxy is set up, and the way that the laws of physics work, and how intricate and amazing our biology is. I find that fascinating and amazing, and just really beautiful. Some people, then attribute that to some higher power, wherever you come in the world and whatever your religious tradition might be. I just think that that's a phenomenal aspect of the world and the universe. Again, it may be that it's some higher power, and it may not be. I myself, again, am not very religious, but I really respect that lots of people see that same beauty that I think I do and attribute it to a higher power. So in terms of specifically answering the question, I don't really see there being a form of a higher power myself, but I know, plenty of people around the world, and probably many of you watching this do. And again, I don't see those as mutually exclusive. I will add that the places that I think are still challenging to have this discussion is when people don't acknowledge some of the evidence that we have in science. As I've said, I think in the introduction to this class, that science is always changing. Science is not really about the absolute truth. It's about a quest for truth, and it's about something that we are constantly looking for. It doesn't mean we don't know anything, because certainly we know if we throw something up on the Earth, it's going to fall down, and so we can know how gravity works in a pretty amazing way. That doesn't mean we know exactly how gravity works. No, not at all. But it means we know how gravity works pretty well. So that said, there are many things in science that we don't know super well. The very beginning of the universe. How did the universe actually begin? We don't know that. But we have very, very good evidence that the universe started 13.8 billion years ago. We have very, very good evidence that the Earth and the solar system and all the planets formed about 4.567 billion years ago. We actually know it to that precision. It's that amazing. And so there are lots of things in science that can tell us some great things. Unfortunately, there are some groups who don't follow that, or don't look, or don't really learn about those lines of evidence. And I think that's where we currently get some frustration or headbutting between religion and science. But again, I have colleagues here at Boston University who are very religious and still study things like cosmology, like the beginnings of the universe. And again, those are not mutually exclusive at all. So it's a great question.
Do you want to take one more from here and then go
Sure.
to the discussion?
Yeah.
So how do we observe the curve of space? It is really difficult for me because intuition still tells me that space is empty and the emptiness is straight. A curve is quite weird.
So the question is, how do we observe the curve or the curvature of space? It turns out that space can actually be curved. That actual space itself can be curved. That the shortest distance between 2 points isn't a straight line, which is very much easier for us to think about, but actually is a curve. Imagine if there is a curved space that we all know really well. Imagine a globe like the Earth. And you know that if you're sitting in Boston, where Aurora and I are sitting right now, and we want to travel to, let's say, India, right? The path that we're going to travel to get to India is not going to be a straight line, right? Because that would actually require us digging through the Earth to get to India, right? No one does that. Instead, most of the bus will fly, and there you actually take a curved path along the globe to actually get to India. So, and you can imagine just if you were walking along the globe, if you just drew a line from Boston to India, that's still a curved space because you're walking along a curved surface. Same thing can be true of the universe and space itself. And actually things like gravity can actually help to bend space. The question said that like we think of things as straight because space is empty. Well, space isn't empty at all, actually. There are pockets of space that have a lot less material and some that have a lot more material. But space itself is not empty. It is full of material. It's full of gas and dust, the gas and dust that eventually forms stars and planets. And that's true in between stars, what we call the interstellar medium. It's true between galaxies, which we call the intergalactic medium. There's always stuff in space, and some of that stuff can act to potentially slow down the galaxy, sorry, the expansion of the universe, but it can also curve the universe. One of the ways we measure that is by actually looking at how the universe is expanding. There's been a really cool thread on the discussion group about the difference between the age of the universe and the size of the universe. That we actually have, the universe is 13.8 billion years old, and if it was this perfectly static box, then you would be able to see 13.8 billion light years away, because that's how long it takes the light to get to us. But the universe is expanding, and it's not only expanding, it's actually, we have evidence that it's accelerating. And because it's accelerating now, the universe, when light started to travel to us, has actually gotten even larger. And so those same points that we could see are now even farther away. And so we can actually, the parts that we can see are now, roughly 50 billion light years away. It depends a lot on the exact expansion rate and the exact acceleration and all of those kind of things. And how we measure that, both the acceleration and expansion, as well as the curvature of space, is by actually observing objects and seeing the relation between how far they are moving from us, or how far away they are, and how fast they are moving away from us. So the moving fast away from us is actually pretty easy. As we'll see, I think in the next module, in the module on light, we'll see that one of the things that happens to light or sound as you're moving away, the wavelength gets expanded. So for sound, that makes the pitch go down. You've seen a car go away from you, it goes, boom. And if you have light, something going away from you, it actually gets a little bit redder as it goes farther away, or as it goes away from you. And actually, as something comes towards you, it gets a little bluer, or the pitch goes up. It goes, things like that. That's called the Doppler effect. And so we can actually look even into these distant universe. We can look at galaxies or objects called quasars that are literally billions of light years away. And we can actually see very easily how fast they're moving away from us. It's a very easy measurement. I mean, I could teach an undergraduate student or a high school student to do it in less than a day. Very, very easy technique. What's way harder is to actually say then what the distance to something is. And we use a ton of techniques in astronomy to tell distances, all the way from distances of stars in our own galaxy. So one of the things that my students in my research group have to do is actually measure distances to stars, and that's hard. And there's lots of different ways to do that. We could spend probably a whole hour talking about that. But as you go to farther and farther away distances, we have to come up with more clever and different techniques. One of the ones that's used most prominently right now in the distant universe is actually using supernova, a special type of supernova called supernova 1A. It's actually an object called a white dwarf, we think this is what they are. Object called a white dwarf, which is what the sun will become when it runs out of gas. It's about the mass, a little bit less than the mass of the sun, but the size of the Earth. So it's a very, very dense object. And it has a companion star, a binary companion. And that companion is actually putting material onto the white dwarf. And eventually it puts so much material that the white dwarf explodes. And when that happens, it produces a ginormous explosion, one of the most powerful explosions in the entire universe. And we can then see it from very far distances. And it turns out that we think the way that physics of that process works, that those objects give off about the same amount of light every time they go off. So they're the same brightness. It's like you had a 100-watt light bulb, and if you were to go, put a 100-watt light bulb at different distances, you would see that, like, if you knew that it was 100 watts, even if you couldn't see how far away it was, you would know that the dimmer one would be the farthest away, and the brighter one would be the closest. And we do the same thing with supernova. So we can actually then trace galaxies and these objects called quasars throughout the universe, and especially galaxies that have a supernova that goes off in them. We can see how fast they're moving away from us, how far away they're moving from us, and that tells us how the universe is expanding, how it's accelerating, and how it's curved. So, wow, lots of information there. Probably might have more questions. Sweet. Okay, we're going to go to one from the discussion boards.
All right, so the first question from this discussion is, I have a question about gravity and the speed of light. If a star is sufficient mass to become a black hole, would there be a location in the core of the star which holds the event horizon of the future black hole? From my understanding, the star that becomes a black hole compacts to a single point with a gravitational field that won't allow light to escape. Is this based off density, or is it just the mass alone that creates the gravity well?
Oh, wow. Okay, so Aurora asked a question about, I don't know how easy it is to hear her, even though she's sitting almost right next to me. Don't know how easy it is to hear her, but, oh, okay, perfect. So I think everyone heard. The question is about a star that has enough, is basically enough mass to become a black hole. And when we talk about stars, we'll briefly talk about one of the end stages for stars that are, roughly about 20 times the mass of the sun. Is that when they die, they will actually also explode in a different kind of supernova. But some of them will, what's left at the end will still be so massive that the star cannot support the gravity. And so the gravity will suck that material in, and eventually it will get really dense enough. It will come close enough in that it will be so massive and such a small amount of material that it will actually become what's called a black hole. And what a black hole really is doing is it's actually taking space and curving it in on itself. So just like we did in the demo, remember, from Module 2, if you've already watched that, we had this big sheet. We learned how gravity really works, right? It's something that's bending space, right? And so for a star or something, it just puts a dent in space-time or in space. And a planet is orbiting around. A planet just thinks it's going straight, but it's actually moving through this curved space. Okay, you took a black hole and you took that bowling ball that we put in the center of that big sheet, and you just stretched it until it went all the way down. You would actually kind of collapse space in on itself. You would actually have so much gravity that space would close in on itself. That's exactly what a black hole is. You've actually created so much gravity and you've bent space. It bends, it bends, it bends, it bends, and it basically bends back in on itself. And so a black hole is what we call a singularity. It's a single point in space. It has mass, but it has no size, no volume, no length. We're using length as size. Size means length in this class. So this thing has no anything, just mass. And that's because it's bent space in on itself. That means nothing can get out. Nothing, no particles, no spaceships, no light. Even light can't escape because you've actually collapsed. You've had so much gravity that you've collapsed light, the space in on itself. Now, the question asks, does this black hole exist in the star to start, I think. So from the beginning, if you have a star that's really massive, does it actually have a black hole at the center? And it used a term called the event horizon. And the event horizon is it's the sphere of influence around the black hole. So the black hole is a single point in space, but there's an event horizon that is basically the point of no return. It's where the gravity is so strong that once you pass that, you aren't coming back. So even light passes in through the event horizon, it's not coming back. And so the person asked, is that, do you have a star with a black hole singularity and a point source in the center? The answer is no, that doesn't actually happen until the star kind of fails. And that's partly because even though the star has enough mass to become a black hole, it hasn't gotten dense enough. And that's because when a star is alive, it is actually going through a nuclear fusion process that's very similar. In fact, it's exactly the same physics as a hydrogen bomb, an atomic bomb, an actual hydrogen bomb. It's smashing together hydrogen, and in that process it is creating helium and then a bunch of energy. And that energy is actually allowing the star to actually stay pressurized to actually stay upright. You know, there's so much mass in a star. Even a star the size or the mass of the sun, you know, gravity wants to pull that thing and shrink it down to nothing. But because the sun is going through this series of fusion reactions, it's actually keeping the sun its own size. We call that hydrostatic equilibrium. And so the sun is staying the same size because its insides are pushing out. And so that actually prevents even a more massive star from becoming a black hole. Once the star runs out of fuel, runs out of hydrogen gas, it no longer can keep the star, you know, at its current size, and the star will collapse. And that's when you can get things like supernova explosions and eventually black holes.
We'll do another.
Yeah, let's do another one. Yeah.
Kepler's law states that period squared is proportional to semi-major axis cubed. In the lecture, we said that when t is expressed in years and a is expressed in astronomical units, the proportion sign can be replaced by an equal sign. I was wondering if this is entirely correct, as the astronomical unit, if I understand correctly, is historically defined as the average distance between the semi-major axis and the semi-minor axis. And that would mean the semi-major axis of the Earth moving around the sun is a bit bigger than 1 AU. Is this correct, and how big is the error we're making in this approximation?
Oh, that's a good question. I think there's maybe a slight confusion in that question. The semi-major axis, that 1 AU is the semi-major axis of the Earth, and that is the average distance that the Earth is in its orbit. So it means that the Earth isn't always 1 AU from the sun. It's sometimes a little farther and sometimes a little closer, but on average, it's 1 AU. Now, the Earth's orbit is pretty circular, so it doesn't get a whole lot closer to the sun and a whole lot farther, but as we saw with Kepler's first law, the Earth orbits in an ellipse, and so it does spend a little bit of time closer to the sun when it's moving a little faster, and there it's less than 1 AU. And when it's a little farther from the sun, then it's a little farther than 1 AU, and it's moving a little bit slower. So I guess there's a little bit of confusion in the nomenclature, but it means that the period, which is defined as, you know, the time it takes from one orbit, is defined just based on that semi-major axis, which is the average distance. So the period squared equals the semi-major axis cubed is actually an exact relation, again, under the caveats that we talked about in the lecture, that you're around a solar mass star. Actually, and if you go through the math in detail, that you're actually around a planet that's of much smaller mass than the star. So in the Earth's case, that's totally fine. And that you express it in units of years for the period and astronomical units for the semi-major axis. All those caveats, that's equal. And I think we have is it in the challenge problems that we have the full expression for?
Yeah.
So if you're interested and you want to do some of the challenge problems.
It's also in the simulation solution.
Oh, nice. Okay, so Aurora was just saying that in the simulation solution set, you can actually see the full Kepler's third law. That isn't the nice simplified one that we're using for the class, but for those of you who want to learn a little bit more, you can see the full Kepler's third law in the simulation solutions or in one of the challenge problems. And certainly, if you just Google or look on the internet, you can actually see the full derivation if you want for Kepler's third law, which is a little bit more complicated, but not a lot. Okay.
Keep going.
Yeah, sure.
How exactly did early astronomers plot the positions of planets in space and therefore be able to determine the shapes of their orbits? I can see how they can plot positions against the stars to get angular changes, but how do they fix the distance from the observer?
Ah, okay. Well, there's a couple different ways. To be honest, Aurora and I had to talk about this a little bit beforehand to remember, because nowadays what we do for at least the big planets is we can actually bounce radio signals off them, and they return, and if we know what the speed of light is, we know exactly how far away the planet is. It's actually pretty clever, pretty easy technique. But we still actually use a similar technique to the way that Kepler did it when we were looking at, say, orbits of asteroids or things like that, where we don't necessarily shoot radar beams off of them. And that is actually one of the ways Kepler did it is just through geometry. I mean, he was able to take a planet like, let's say, Mars, and he could actually see from the data he was using, which was taken by the astronomer Tycho Brahe, that Mars would go this far away in the sky, and then its next point would be over here, and then he could say, okay, well, that is the full extent of the Martian orbit, all right? And then using geometry and using knowledge about how far the Earth was from the sun, he could actually just draw a triangle and say, no, what the angular separation of these 2 points is the sky is. And actually then I know, if I know the distance from ourselves to the sun, I then can just use geometry to calculate what the linear distance is between those 2 points. It was actually just simple geometry. The other method that Kepler used was just really a guess and check version, where he just said, okay, well, I know what the orbits should be. And he actually started with circles and then moved to ellipses when he figured out they should be ellipses. But he just basically said, I have all these data for how the planets are moving through space and through the sky. How big do I have to make my orbit to fit the data? And in fact, we also do that with asteroid orbits and things today too. When we actually go to derive an orbit for a new asteroid or a comet that we discover, we actually, one of the things you solve for by literally just fitting the data is the semi-major axis, how far it is from the sun. So, one of the things you have to do to, say, name a comet, it's one of the few astronomical objects you can still name, say, after yourself if you discover it. But the way you have to do it is you have to be the first one to identify it, and then you have to actually give an orbit. You have to actually calculate its orbit. And the way you do that is by taking multiple observations and seeing how it moves through the sky, and then literally fitting an ellipse to it. And as part of that ellipse fit, you actually get the semi-major axis. One of the other ways that Aurora and we actually looked up, I didn't actually know this beforehand, but we looked up another way that people did this, actually I think after Kepler.
But only like 20, 30 years.
But only a little bit. So it was about the same time as Kepler, so in the 17th century. They actually did a really cool parallax technique. And we haven't talked about parallax. All of you use it, whether you know you do or not. If everyone takes their finger and puts it up in front of their computer, and then you blink like that, and you watch, even though it looks like you're not seeing my finger move, I'm seeing my finger move. When I blink, my finger looks like it's moving back and forth. That's parallax. It's because my eyes are separated by some distance, and when I hold my finger out, one eye sees the light going this way, and the other one sees the light going this way, and so it actually looks like my finger has moved. And my brain actually takes that signal. My brain only sees one finger when I have both eyes open, unless you're dizzy or something. And my brain takes that information, and it tells me how far away my finger is from my face. And that's a parallax distance. We do the same thing in astronomy. We do it to measure distances to stars, but some 17th century astronomers did this to actually measure the distance to Mars. They, just like their two eyes, they put one astronomer on one part of the Earth and another person on the other part of the Earth, and they just like two eyes, and they looked up at Mars, which was like the finger, and they actually took images of Mars at exactly the same time, and they could actually see how Mars's position against background stars that are so far away that they don't look like they move, how it changed depending on where you were on Earth. And that gave them a very good estimate or measurement of how far away Mars was at that point. So very clever, very cool technique. They had to do it at exactly the same time, so they'd have good clocks and all that, but really clever technique, and something I didn't know was done until we looked it up.
So the last question from the discussion is two, actually. Are pulsars different from exoplanets? All I know is that the pulsars are detected by radio telescopes, and for exoplanets you use optical telescopes.
Oh, that's a good question that has a bunch of things in it. So the question is really, are pulsars different than exoplanets? And the answer is yes, although it's there's a complication in there. But let me tell you what a pulsar is. A pulsar is a type of object called a neutron star, and that's what happens when a really massive star, something probably more massive than about 8 or 9 times the mass of the sun, but remember less than about 20, because then it becomes a black hole. When a star like that dies, what's left at the end is something that, again, is so much mass that it gets very, very compact. In fact, all the neutrons pack as tight as they can, and so we call it a neutron star. It is something that's about the mass of the sun, but about the size of a city, about 10 kilometers in size, in radius. So it's very tiny, and so has enormous surface gravity, if you imagine. And these were hypothesized, 50, 60 years ago, but a class of them was discovered, I believe, in the late 60s, because they actually rotate like this, and they have some of them have very strong magnetic fields, and some material can get shot along those magnetic fields, and if that magnetic field points kind of towards us, we actually get a pulse of light. We get a pulse of light in the radio part of the light spectrum, and so you imagine you get pulse, pulse, pulse. And so there was a graduate student who at the time, her name was Jocelyn Bell, and she was a graduate student in England, and she was doing this giant radio telescope survey, and she actually first identified these objects because they were creating these pulses in her thesis, in her PhD thesis data, and she actually kind of thought they were annoying but interesting because they were constantly there. And so we know that these pulsars now are neutron stars that are rotating and have these strong magnetic fields, so we can see them. So they're not planets at all. The confusing thing is actually the very first exoplanets. We're not going to talk about this much in this class. Very first types of exoplanets were actually discovered around pulsars. The reason that most people kind of don't talk about them or ignore them is because, remember, I didn't say this, but a pulsar is probably the after product of a supernova. That the star actually explodes, and then what's left turns into a pulsar. In that explosion, you would probably destroy any planets. And so the planets that have been discovered around these pulsars were actually probably formed after the supernova explosion. So they're a very different type of planet than we see around our own sun or around these countless other suns that we're going to talk about a lot more in this class. So pulsars themselves are basically the remnants of stars, whereas exoplanets are planets around other stars. They're kind of two very different things. Now, the question was also asking about the types of telescopes we use. So certainly pulsars, we use radio telescopes. I think actually there's a pulsar in the Crab Nebula, and I think you can actually see that in other wavelengths. I think you can actually see the pulse in optical or other wavelengths as well. So it's not exclusively radio. For exoplanets, you actually don't just use optical telescopes. You can use infrared telescopes. There are people who are using radio telescopes to search for them. I'm trying to think if I can think of a discovery yet. Not sure I can think of a discovery yet, but there's certainly people who are looking for exoplanets using radio telescopes. There are pieces of X-ray exoplanets that have been detected in the X-ray. So we've seen evidence for exoplanets and actually exoplanet atmospheres and maybe even magnetic fields in the X-ray. So exoplanets, although predominantly has been in the optical and infrared, really actually spans the entire electromagnetic spectrum as well. But that's a really good question.
So the second question is the news about a 10-year mission to find life on Europa. Defining life is not easy. Why not propose to send a space mission to view Earth from afar? Maybe look at Earth, then look at Venus and Mars and other planets in our solar system and compare spectra to find the signatures of life, say oxygen, methane, etc.
It's an awesome question. Hope you guys all heard that. It's basically, saying that, I said in the video updates that NASA is planning this really exciting mission to Europa, and just a couple weeks ago announced all the instruments for the mission. And one of those is to actually look at Europa and both detect the particles coming out of these crazy vents. Europa is this moon of Jupiter that looks like it has a subsurface ocean made of water, maybe probably even salt water. Europa also looks like it has a heat source, which is keeping this what should be frozen moon liquid. And it also has organic material, which we can actually see scattered across the surface. So it has actually all of the things that we know are important for life. We don't know if it has life. But one of the things that happens in Europa is looks like it shoots out some of this water into space. And so we're not going to actually land a spacecraft on the surface, but we can fly very close to the surface. And when there's things spraying out into space, we can actually collect them. We can analyze them. We can analyze the gas. We can analyze the actual particles. We can also take a spectrum, which we'll learn a lot more about in the next module, but we can actually analyze the light coming from the surface. That'll actually tell us something about what it's made of and what different materials are on the surface. We can do that very, very well, and even better if we're flying a spacecraft right over the surface. And so it's going to be really exciting. It means that we will learn a lot more about what Europa is made of, what is inside of Europa. Does it mean we're going to discover life? No. Would that be awesome? Yes. Probably be like the greatest discovery of all time. Really demonstrate that there's life elsewhere would be huge. But I don't know if it's going to happen, but it's certainly something we should go do and look, and it looks like we're going to. But this student asked this awesome question about, well, why don't we go and look back at the Earth, send a spacecraft out into space, look back at Earth, take a spectrum. We know there's life on Earth, so maybe we could use that information to figure out what we should look for around other worlds. And then we could compare that to like Mars or Venus or worlds that we haven't found life on, and see what's different. And in fact, people have done this. There are a lot of spacecraft that are pointed down looking at the Earth, many of them for science, some for not science, things like spying on other countries, and things like that. So we actually have done that experiment. One of my good friends, who's a now professor at Amherst in Massachusetts, he has actually done a few papers thinking about this. And he actually uses that information to then think about how would we go and look at not just Europa, but look at worlds orbiting other stars, because we actually now are right at the edge of technology where we could look very easily for things like oxygen or methane in the atmospheres of other planets. We've actually detected atmospheres of other planets, and we'll talk a little bit about that later in the class. But we've actually detected things like sodium, things like water in the atmospheres of planets orbiting other stars. But at least for life like we have on Earth, one of the smoking guns would probably be to find oxygen, and certainly oxygen combined with methane would be an amazing thing. Most of the oxygen in our atmosphere on Earth is actually from life. Very little of it, almost none of it, actually comes from natural causes, geologic outgassing or things like that, where we get a lot of the other atmosphere that we have. Most of it comes from life. Turns out methane, the methane we have in the atmosphere, also comes from life. And it turns out that when you put those two gases together, those two molecules together, they actually don't like to live together by themselves. They actually like to combine. And they combine to make things like water and CO2 and things like that. Methane is CH4, so it's carbon and hydrogen, and of course oxygen is just oxygen. So you combine those together, you can actually make carbon dioxide and water, and that is what happens when you mix those two things together. So if you have those things being produced readily on the surface of a world, and we know that life produces those very readily, and you see those in the atmosphere, they must have just been produced. And it tells us that maybe you've got something like life happening. Now, if we saw that around an exoplanet in the atmosphere, would it be, again, 100% evidence that there's life? No. But would it be 99% chance that there's life? Yes. And would it be super exciting? Yes. And in the next decade, maybe 2 decades, but in the next decade, we will launch the next large space telescope, the James Webb Space Telescope, and it is going to have the capacity to measure things like oxygen and methane in the atmospheres of nearby exoplanets. And so if things like oxygen and life like we have on Earth are common around exoplanets, we will see that in the next decade. Certainly in 2 decades, I think we will know if life like we know it is common on terrestrial planets in the solar neighborhood, within, I don't know, 10 light years or so from us.
So back to the Google Hangout.
Yep.
We have a question. Could you tell something about the recent discovery of Higgs boson particle at CERN? What does it mean for astronomy, and is there something we should rearrange in our beliefs so far?
Well, so the question's about the Higgs boson. I'm going to be totally honest that particle physics is starting to get out of my specialty. I can tell you that was a very big discovery because one of the things I do know is that what we understand about physics has some very clear rules about how at even the particle level or the quantum level, and we get to really tiny things, how those kind of proceed. We call it the standard model of physics, and it's an idea. It's an idea that's, I would say, now been elevated from a hypothesis, which is really just a great idea, to a theory, which people use very incorrectly. A theory is something that has a lot of evidence to back it up. So a lot of people you hear colloquially say, "Oh, well, that's just a theory." Well, of course, that when you say that, that means, oh, you have a lot of evidence. That's a good thing. It's not a bad thing, but people don't understand the difference between those words. So the standard model is actually a theory. There's a lot of evidence that shows that our understanding of small scale physical universe is good, but there were some problems with it, and one of them was that it's missing some particles, and the Higgs boson was one of these particles that was predicted to be something that helped solve one of the problems in the standard model. And the discovery of that at CERN really has led to a Nobel Prize, and part of the Nobel Prize that was given out was because this really helped solve a few of the problems that were still in this kind of standard model in physics. Does that make us have to I think the question said, do we have to rethink?
Rearrange our beliefs.
Right.
So far?
No, it actually, in more than anything, it just confirms many of our beliefs that what we thought was happening and working in physics works. So that doesn't mean there's many more problems out there. In astronomy, I mean, at the particle physics level, one of the things that right now we don't know much about is the dark matter. Appears that the matter in the universe is made up of a very small percentage of small percentage of the matter in the universe is the type of stuff that you and me and Aurora are made up of. Most of it is made out of something we don't know. We call it dark matter because we don't see it, and it's not very satisfying. We know it is there. We're pretty sure it's there because because it's massive. It has gravity, just like we've learned in Module 2, right? So like something with mass, you have another particle with mass, it attracts it, and so we actually see evidence for these gravitational interactions with something we don't see. So that's troubling, but I would say more and more over the last several decades, we've really built up a huge body of evidence that something is out there. And the kind of best idea for what it is probably another subatomic particle or very tiny particle that is very massive, but doesn't interact well with other particles. And so it's really hard to see. It doesn't produce light very easily, at least. But there are a lot of people working very, very, very hard to try to actually figure out what this stuff is. And I also think that's something that probably we will know much better in a few decades. I mean, it might be next year. It might be tomorrow, for all I know. But it also might not be for a little bit. But it's something that people are investing a lot of time, a lot of thought, a lot of money into. And I think it's pretty cool because it really is something that informs us about what our universe is made of. In our own galaxy, we think that about 90% of the mass of our galaxy is made up of this dark matter. 90%. So it's not like half is missing. It's almost all of it is missing. 10% is made up of stars and gas and things like you and me, normal atoms, protons, electrons, neutrons, and all the elements that we know from chemistry. That makes up only about 10% of the matter in our galaxy. So crazy.
So there's one more question in the discussion, or in the questions part. It says, for me, somehow science is like a sandcastle. There is no guarantee that all of our theories today will still be true in its scope tomorrow. E.g., we believe that G is a constant, but who can say that it will be the same value tomorrow?
Awesome question. Awesome question, or a comment. Yeah, it's like a sandcastle. I guess the analogy is that if science is like a sandcastle, the ocean can come and destroy it. I'm not sure I believe that that's the right analogy. I'm not attacking your analogy. So it's a fun analogy. I think science is more like a rock wall or something that a little bit gets knocked down over time, and so you have to build it back up. And when you build it back up, you probably know a little bit better how to do it. The example that the student used, that the constant G that we use in gravity, for hundreds of years we have thought that's constant. There have been numerous tests to try to show that it's not constant, and every single one has demonstrated that it still is constant. Does that mean it's still constant? No. There may be certain conditions where gravity behaves differently. We know that already, that it behaves differently than Newton came up with it hundreds of years ago. Einstein had to come up with the theory of general relativity because Newton didn't understand that space was curved. And there was a whole new mathematics and a whole new formulation of gravity that was required to really explain that. So I totally agree, though, that science is this ever-moving target. Some things are very well known. We understand really well how light works, mostly. We understand how gravity works, mostly. We understand how many things work, but it's totally right that many of the things that we know today may be different tomorrow, and certainly may be different in 10, 20, 30 years. You look back, and I showed this example in Module 1 of an astronomy textbook that just was totally wrong. And there are textbooks that we even get today in astronomy that have things that aren't correct in them because things have already changed so quickly. For me, that's the excitement of science. And it's one of the things that I want to demonstrate in all of my classrooms, including an online classroom like this one, is that science isn't a class like I think many of us had while growing up, where we learned a bunch of formulas, we learned how to balance chemical equations, or we learned a bunch of biological terms or processes, and we spit those back out on a test, and that was like how the world works. That's not science at all. Science is a process. It's, again, a quest for truth. It is not the truth itself. It's what keeps me in a job. It's what keeps, it's why we train graduate students like Aurora to become scientists. because we get to think about all these questions, and we live, many of us who are in this MOOC live in societies around the world that support science, that support our ability to think about how the world works, to think about the universe we live in, to think about where we come from. And yes, it's a moving target, and that's what's really exciting about it, is that we're constantly learning new things, but we're also learning about how we didn't understand things. And that's really exciting. So I love that comment. I think a sandcastle, the reason I don't like that analogy is when the ocean comes in, it totally destroys the entire sandcastle. And that doesn't happen often in science, that something is totally destroyed. Usually a little bit's knocked down because we learn something new. We have to build up from usually what's already a pretty good foundation. Or maybe nothing gets knocked down at all, but we build a new turret on the sandcastle, or put a flag in the top or something like that. Or maybe we build a moat around the side. Sometimes we just build on the existing ideas, on existing theories. So certainly I love the comment though. It's really true. Is there anything else? Okay, unless there's any final things, I think that takes us just about to an hour where we start from where we started. Thank you for really, really amazing questions. Thank you for Aurora for helping out with this. Really, really fun hearing your questions and getting to chat with you. We will do this again, I think, in 2 weeks or so. We'll let you guys know when we're going to do this again. Please it's on the syllabus when the next one is. Keep asking questions. Keep the discussion forums going. It's been really fun participating in that this time. And ask Aurora and I lots of questions. And enjoy Module 2 and Module 3 when we launch it next week. All right. Have a great rest of your week, and I'll talk to you in a couple weeks.